In this video, we're going to calculate another Jeffreys prior for a vector parameter. And the particular one that we're going to work with is a multinomial distribution. So you can see there the distribution sheet, and the multinomial distribution is a discrete distribution. So let us recall the multinomial experiment. A multinomial experiment has the following properties. First, there are n identical trials. That should seem familiar to us. That's the same as what happens in the binomial experiment. The second requirement there is that the outcome of each trial falls into one of k classes. The binomial experiment itself is a multinomial experiment where k is 2. But in general, we can have, 1, 2, 3, 4, 5, or however many outcomes. But for any one experiment, that number has to be fixed. And then thirdly, the probability on any one trial that the outcome is class I is pi. So if our k were 3, for example, then the outcome of each trial would fall into one of 3 classes. Maybe we do an experiment and we get one of 3 colored marbles or something. And in that case, k is 3. And so if we do this 8 times, then maybe the first class would correspond to a red marble, the second class would correspond to green marble, and the third class correspond to black marbles, or something like that. And so P sub 1 in this case would be the probability that we get a red marble on any one trial. P sub 2 would be the probability that we get a green marble on any one trial. And P sub 3 would be the probability that we get a black marble on any one trial. And those probabilities stay the same for each trial. And then fourthly, you can see there that the trials must be independent. And then fifthly, the random variables of interest are the y1, y2 until yk. So in our example, y1 would be the number of red marbles, y2 would be the number of green marbles, and y3 would be the number of black marbles out of the 8 marbles that we get. So you can see that what must also be true is that the sum of all the y's must give us little n, which in my example is 8. Okay, so that is the multinomial experiment, and the distribution that governs this experiment is the multinomial distribution that we just looked at. Notice here that we have our random vector y, which records the number of trials that fell into the first class, the second class, and so on. Then we have our parameter vector p. Here is the PMF of the multinomial distribution. But now recall that whenever we calculate the Jeffreys prior, we're going to regard the yi's as fixed or constant and the pi's as the variable. And just some other facts, each pi must be greater than 0. The sum of all the pi's has to be 1. That makes sense because, like in our example, anytime you get a marble, it's got to be one of those 3 colors. And then also the sum of all the yi's has to be n. Now the mean of this distribution is little n times that vector p. And I think I wrote k equals 3 here because in a previous video where I explained this, I probably alluded to the example. Okay, so now let's first work on calculating the Fisher information matrix. So remember that to do that, we've got to first look at the log likelihood. And so going off of the likelihood function, remember we're not going to refer to it right now as the PMF. We're going to refer to this, this part here is the likelihood function. We're taking the log of that. And then once we do a little simplification and apply some of the log properties, that gives us what we see there. Next, we need to calculate some partial derivatives of that log function. So notice here that we're calculating the partial derivative with respect to p sub j, where j is just some natural number from 1 to n. And if we are going to use the computationally friendly formula, we'll also have to calculate another partial. So that's the next step. Now let's calculate the partial with respect to I. If I is different from j, then we're just going to get 0. But if I is equal to j, then we get this. So now we have the second partial derivatives. And so the next step is to put together the matrix, the Fisher information matrix. And so remember, what's helpful there is to list the parameters across the top along the columns and then also along the rows, because that just serves as a mechanism to help us keep straight what goes where. And remember that when we're deciding what goes in each element, it's the partial with respect to whatever's in the column first, and then with respect to whatever's in the row. But in this case, since it's 0 anytime the I is different from j, then in the off diagonal entries of this matrix, we're just going to have zeros, right? We've got a 0 there and a 0 there. And then, so we just have non-zero values down the diagonals. When they're both 1, you get this, and when I was 2, and so forth. And notice that this is a k by k matrix, right? Remember that common dimension, the number of rows and the number of columns for this square matrix is determined by the number of components in the parameter vector. And also, if we're using this computational formula, each one of these terms individually have to have another negative in front. And so I just put that out in the front, the entire matrix. The next step is to apply the expectation operator to each entry in the matrix. And I just noticed that I need to correct some notation here. So let's put the vector y up here. So now we need to apply this expectation operator to each entry in the matrix. And recall that the expected value of y1, that will be the expected value of the first component of this vector, and that's just going to be n times p1. And then the expected value of y2 is the expected value of the second component of y, and that's n times p2, and all the way down to n times pk. And then when you simplify, we get the Fisher information matrix of what we see there. And now the next step would be to take the determinant of this Fisher information matrix, but since this is a diagonal matrix, the determinant is just going to be the product of all the diagonal entries. And so we're basically ready to determine the Jeffreys prior. So the Jeffreys prior is proportional to the determinant to the 1/2 power, and remember that determinant is just the product of the entries along the diagonal, and then that raised to the 1/2 power. And from here we just keep simplifying, and we get what you see there. And at this point it would behoove you to pause the video and go look at your distribution sheet or wherever you refer to check out distributions. This prior distribution, this Jeffreys prior, is one that is well known. You're looking for the distribution of a vector, random variable, with the property that each component must be from the closed interval from 0 to 1. And as it turns out, that is what we call the Dirichlet distribution. And it's a Dirichlet distribution with parameter alpha. So since we know that it's a Dirichlet distribution, let's go look at that distribution on our distribution sheet. Now, since each component is from the closed interval from 0 to 1, this Dirichlet distribution is going to be in the continuous distribution list. So let's just scroll down through here, and there it is. So the Dirichlet distribution is what we see there. So again, you have to think of the x's as our p's, and then the alpha is the parameter. And similar to some other distributions, we can focus on the power alpha I minus 1 on the xi in that product. And so to determine each component of the parameter vector alpha, we're just going to look at that power and add 1. So if we look here where that power has been boxed in red, we just add 1 to that, and that will just get rid of the minus 1. And so I've highlighted the 1/2 because that's the parameter for, in this case, each component. So the alpha, the parameter for the Dirichlet distribution is the vector of 1/2. The only thing that we need to determine now, if we want to nail down exactly what the Jeffreys prior is the normalizing constant, the number that goes in front. So we're focusing on that gamma of alpha naught divided by that product of the gamma alpha. And that's what you see that I've done in green here. Recall that gamma of 1/2 is the square root of pi. And then also we need to recall what is that alpha naught. Notice that the parameter of the alpha starts with alpha 1 all the way until alpha k. But what is alpha naught? Well, alpha naught is the sum of alpha 1 plus alpha 2 all the way to alpha k. So in our example, since we've got all 1/2, the sum of all of those would be k times 1/2, and that's why we did this here. And then divided by that product of all the gamma of alpha i's. And I have a note here to double check, but I'll let y'all do that. So the normalizing constant is this, and so that gets us to the Jeffreys prior.